the Electronics Cooling webinar, What Burns Me Up? Digging Deeper into SEMI-THERM. Electronics cooling has developed up-to-date information and practical articles on thermal management since 1997. This webinar is presented by Roger Stout, Research Scientist, Packaging Technology, Corporate R&D for ON Semiconductor. Roger Stout is the charter employee of ON Semiconductor. He received his BSc in Mechanical Engineering at Arizona State University in 1977 and went on as a Hughes Fellow to earn his MSME at the California Institute of Technology. In his 35-year career, Roger has authored and co-authored 61 technical papers, the vast majority related to thermal characterization of semiconductor devices. He holds 6 patents and has been a registered professional mechanical engineer in the state of Arizona since 1983. This webinar will be interactive. You will be able to ask questions and we encourage you to participate. Take a look at your GoToWebinar navigation pane. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. And to maximize the screen, click the middle button. We will present the topic for 45 minutes, followed by a 15-minute question and answer session. Now Roger will begin the presentation.
Well, good morning. I developed a cold in the last 2 days, so I hope that doesn't impair my ability to talk. But we'll get started. In my abstract, I claimed that thermal errors occur at all scales, from semiconductors to the whole planet. What I decided to do is to start big, literally at the global scale, and work my way down. Along the way, I'll definitely pick on a couple of my pet peeves that may not be exactly thermal errors, but I hope you'll see that even as we progress down in size, many of these thermal errors do relate to electronics, electrical design, or electronics packaging. Let's start with this infamous global warming hockey stick chart you may have heard about or seen in Al Gore's An Inconvenient Truth. The problem here is correlation is not causation. The assertion was that we are responsible for increasing CO2 and that increasing CO2 causes global warming. The inconvenient truth seems to be that historically at least, high temperatures tend to precede high atmospheric CO2 content, not the other way around. As I researched this subject on the internet, I found a variety of opinions that over the last 450,000 years, there's been anywhere from a 200 to 1,000 year lag between increasing ocean temperature and a subsequent increase in atmospheric CO2 concentration. The one thing that's certain is that atmospheric CO2 plays a role in a positive feedback loop with global temperature. If I'd had ready access to the raw data, I had originally been thinking I might talk about how you could apply a fast Fourier Transform analysis to the CO2 versus temperature data and sort it all out objectively, but I don't. And anyway, all that changed when I read that in a single hour, the Earth receives as much solar energy as the entire human race uses in a year. So I did some back-of-the-envelope calculations that actually shook me up. I thought for anyone interested in long-term thermal management trends, this would be the topic. When you were a kid, did you ever run across that brain teaser question that went something like this? You've got a big pond where lily pads grow. The area covered by the lily pads doubles every day. The question is, on the day you happen to realize that the lily pads are covering 0.1% of the pond, how long before the pond is entirely covered? The answer is you've got 10 days, that's all. Here's a graphic of basically the same problem, only I've tuned the numbers just a bit. You've got a big pond, and there's this stuff that grows at a fairly modest rate. Daily growth isn't even double, it's just 30%. On one particular day, you notice that the total area covered is 0.016%. That little speck there really does have 0.016% of the area of the big circle. Here's the question. How many days before that 0.016% speck grows to 0.1%? Answer, 7 days. How about to 1%? Answer, 15.5 days. How about until the pond is covered? Only 33 days. There's one other speck I want to throw on there just for visual reference. This speck is only 0.0034%. That's less than 1/4 the size of that original 0.016% speck. And that's what the pond coverage was just 5.5 days earlier. Okay, this graphic is an allegory for global energy use growth. If you're really interested, I might have a little bit more time to go into some of the details during the Q&A following the presentation. The big picture is that Earth's biosphere manifests an essentially perfect balance between energy in and energy out. A couple of gross variables, planetary albedo and infrared emissivity, set the balance point between incoming solar energy and outgoing blackbody radiation, the result being the average temperature we realize on Earth's surface. If you're like I was before I did this analysis, I knew energy consumption growth was bad from a resource and environmental pollution perspective, but not from a raw energy perspective. Well, here's the truth. Leaving us out of the picture, energy in comes from the sun, and it's very well quantified at 1.1 times 10 to the 17th watts, a number that probably doesn't mean much to you off the cuff until we compare it against our human contribution, which is 1.8 times 10 to the 13th watts. That's the anticipated 2013 global power consumption of the human race. That is 0.016% of the solar energy input to the planet. As a time fraction, that indeed represents 1 hour out of a year. As a sidebar, could we even collect this much energy? If we covered just 1% of the total land area of the planet with 16% conversion efficiency solar panels, and if we factor in only 33% of the available hours per day, we could only convert 0.016% of the total solar energy. In other words, we're already using as much energy globally as is theoretically available from renewable sources, given some admittedly swagged assumptions. Worse yet, look at the growth rate. According to British Petroleum, annualized energy use growth rate between 2001 and 2011 was 2.7% per year. I also went back and found figures from 1956, the year I was born, at barely perceptible 0.0034% spec on the earlier graphic. And rather incredibly, the annualized growth rate for the last 56 years has been 2.7%. Compounding 2.7% per year over a decade yields 30.5% per decade. That completes the allegory of that earlier lily pond graphic, which I've here converted to actual years. Okay, so what's so special about 0.1%, supposing that we could generate that much energy? It is, after all, still a whole lifetime ahead. It's special because I now have a granddaughter, and 0.1% is a number that she's going to see in her lifetime. It's kind of like the fiscal cliff, only a bit more life and death, not trying to sound too dramatic. Again, here's a quantitative perspective. I deal every day with heat flux into and out of surfaces. Treating the ocean as a static object, it's very simple to calculate the diffusion of heat over time and depth. That is, how much would the average surface temperature of the ocean go up? How deep would the heat penetrate? And how long would it take for a mere 0.1% of the solar constant? The numbers are rather eye-popping. In a single year, 0.1% increased solar flux would raise the average ocean surface temperature by 0.8 degrees C to an effective depth of about 2 meters. Granted, that's a simple no-mixing or pure diffusion model. If you allow for ocean mixing, the effect will be somewhat diminished. But at the other extreme, if you assume thorough mixing of the top 100 meters of ocean depth, which seems to be a reasonable number based on current oceanographic data, a continuous 0.1% excess energy input would raise that mixed top layer by 1.5 degrees C over a century without the compounded growth rate over another century. And it would be 6.6% if you did do the 2.7 annual compounding. These are environmentally big numbers. They may not burn me up, but they're going to burn up my grandchildren, especially if I didn't do anything when I had a chance. Do you see the difficulty? Till now, I've always believed that renewable energy was a nice idea, and we should supplement our conventional energy with renewable as we go, recognizing that eventually we'd run out of fossil fuels and would have to sustain growth through something like fusion, which is my personal favorite, and I'll talk about that a little later. The thermal error is we simply can't continue to grow our consumption with anything other than renewable, and all renewable is ultimately solar. Otherwise, the raw energy balance in the biosphere will be irreparably disturbed. You know, when I started preparing this speech, I hadn't meant to sound so grim. I guess I did see one happy energy surprise in the data. Between 2008 and 2009, global energy consumption actually dropped. Of course, the 2009 to 2010 growth made up for it, but if it happened once, maybe it can happen again. Given that how we generate our energy matters, in a strange twist, here's where I occasionally encounter something else that burns me up: perpetual motion machines. If they worked, by the way, they'd be non-renewable in the sense that they add energy to the biosphere. But consider this example. A wind turbine converts the energy of moving air into rotating shaft energy. You want to turn that mechanical energy into electrical energy, which takes a generator. But maybe we can improve on the state of the art as follows. Through clever and magical use of rare earth magnets, this generator produces more energy out than it took to turn the rotor in the first place. In fact, so they claimed, if you bought one of these zero-cogging generators to go with your wind turbine, you'd amazingly get twice as much energy out of your turbine than the wind was putting in. Of course, it's a bit tough to directly measure how much energy is in the wind upstream of your turbine, and similarly to measure how much less energy is in the wind downstream of your turbine. So they avoided that issue completely, and to prove the generator claim, they plugged a 1/2 horsepower motor into the wall, inverted the generator's output to DC. I never did figure out why they bothered with that step. And then they burned off the energy in light bulbs. 1/2 horsepower in, 375 watts. 4 100-watt light bulbs out, 400 watts out. Voila, 25 watts of free energy. Now, as a mechanical engineer, I've occasionally been asked to weigh in on perpetual motion machines. In this case, there were so many possible errors, it was hard to know where even to begin. But after an initial criticism that they really didn't have any claim because they really hadn't measured anything, they started adding meters. Now, somewhat cynically, I'll admit I suggested that they really didn't need to measure anything at all. Their best proof would simply be to forget the inverter and plug the motor into the AC output of the generator to have it drive itself. They should use the light bulbs to burn off any excess energy, because we certainly wouldn't want it to get into an infinite energy amplification loop. But heck, if that worked, who needs the wind turbine? Anyway, apparently they couldn't make that work, so plan B was to add meters. Even then, they totally botched it. Among other second-round errors, they measured RMS volts and amps at the wall and simply multiplied, failing to recognize that an AC induction motor like this has an extremely poor power factor. Again, that would be easily enough measured if they made even a modest effort. Better yet, they could directly measure the mechanical shaft power going into the generator, torque times RPM, and compare that with the power out. Third pass conclusion, they have now rephrased their claims to, quote, "We've built a 91% efficient generator for way less money than anybody else ever did," unquote. If so, perhaps they can still sell some of them with their wind turbines. And also, to their credit, I couldn't even find on the internet their original video footage, ads, or claims when I went back to put this little presentation together. By the way, lest you think perpetual motion machines are not found in our business, have you ever heard of a thermionic cooler? Now, to be fair, the common misunderstanding about them would classify them as type 2 machines, which decrease entropy and thus violate the second law of thermodynamics. But practically speaking, the problem is, if you stuff a miniature thermionic cooler inside a semiconductor package in order to lower the junction temperature, you'll have more total energy to get rid of in the end than you would have had in the first place without the thermionic cooler. There's no violation of any laws, but it's probably not the solution you thought it was. It's not that you can't get a lower junction temperature when you insert the cooler. The problem is, to get that lower TJ, your board resistance has to be about 2 times lower than it was before to reject the heat added by the cooler to get the lower TJ. But if you could do that, then you should have just done that. In other words, without adding the cooler, and you'd have lowered your TJ a bunch anyway. This naive use of a thermionic cooler just makes my job harder, and it really burns me up. Okay, let's drop down a huge chunk from the global warming scale and look at the household scale. I live in a very energy-efficient monolithic thin-shell concrete dome house, about 3,000 square feet livable. In the Phoenix area, conventional houses of this size require 7 to 8 tons of air conditioning capacity. I need only 4 tons. I am delighted to say that whereas my neighbors often have $400 plus summer electric bills, my highest bill last summer was $120. Indeed, my average monthly electric bill over the last year was $90. Not at all bad for Phoenix. So, what burns me up? The hot water loop. This is where you continuously recirculate hot water from the tank in the garage throughout the bathrooms and kitchen, so you've always got instant hot water wherever you use it. They said this is economical only if you incorporate it during construction, because you'll never recoup the cost as a retrofit. Well, our dear plumbing contractor, who used PEX tubing, no doubt thought to himself, it's plastic. Plastic's an insulator. So he didn't add any insulation for the lines in the wall at all. Well, the first February we were in the house, we turned on the pump for the hot water loop, and within 2 weeks we had to turn on the air conditioning in February. Here are a couple of infrared photos of the upstairs floor and the utility room wall showing where the hot water lines lurk. And they're right, I did a quick estimate of how long it would take to pay back the cost of an insulation retrofit, and you could forget about it. So, sadly, we don't often use the hot water loop unless it gets cold enough for long enough that we do want to heat the house, which has been about twice in the last 6 years because the dome itself is so well insulated. By the way, last spring I replaced my standard electric water heater with one of those new hybrid units. Instead of simply pure electric heating elements which create 100 watts of thermal output from 100 watts of electrical input, it utilizes a heat pump. It moves 100 watts of thermal energy from the garage air to heat the water, but uses only about 40 watts of electricity to do it. So this past winter, when I did heat the house with the hot water loop, I was literally about 250% efficient, way better than the 100% efficient electric heating I've used in years past. Now, 2 slides back, I broached the subject of infrared scanning. Let me now disabuse you of some common misconceptions about IR temperature measurements that really burn me up. To recap, what you see here are 2 excellent examples of what IR really is good for, finding relative heat losses and temperature differences. Here are 2 more examples. Imaging residual heat in the framing of my garage after the sun has gone down, and tracking bad guys. But there are major caveats in IR imaging. One issue is emissivity, how much a surface absorbs and emits IR radiation as compared to a perfect black body. The problem is, as a general rule, if a surface has a low emissivity, it has a high reflectivity. Here's a picture of my face. Maximum temperature is only about 77 Fahrenheit. Seem a little low? Perhaps. What you might not have guessed, unless I told you, is this isn't my face at all. It's an ordinary mirror. I just happen to be standing in front of it. This is a direct IR image of my face. My point is, if I aimed this IR camera at a shiny, low-E surface and thought I was measuring its temperature, In other words, that was not the mirror's temperature you were seeing in the left-hand image, and it wasn't entirely my temperature either. Here's an image of both hot and cold water lines below my upstairs bathroom, showing where they cross, explaining why sometimes I get a brief shot of warm water from the cold water tap. The irony here is that when I first took this image, I didn't realize that I wasn't even looking at the pipes. I was looking at their reflection in the air conditioning ductwork. Here's another picture, the hot water pipe coming out of my water heater. Where it reads 99 Fahrenheit is where I wrapped it with masking tape, high emissivity, low reflectivity. Where it looks like it's only 70 Fahrenheit is where the bare copper is reflecting the garage temperature all around me. The truth is that most surfaces are going to read a mixture of their own temperature and the background temperature, and you never know a priori what that mixture is. What you see in the image could be cooler than what the camera says. For example, the mirror was much cooler than my face. Or it could be hotter than what the camera says. For instance, the bare hot water pipe. Here's another illustration of the latter. I can assure you the windows on my well-insulated dome house are not -1 Fahrenheit in June. What you're seeing here is the reflection of the night sky, which itself has the IR equivalent temperature of about -100 Fahrenheit, which is totally off the scale in the right-hand image. Now, a good IR camera will allow you to set a global emissivity value and maybe even a background temperature, with which it will correct every pixel in the image. Obviously, even that is going to give you errors if what you're scanning has varying emissivity and varying reflections of possibly varying background. What really burns me up is all the applications engineers out there who have no clue as to what they're actually measuring with an IR camera. This next example of my personal scale attempt to combat global warming also illustrates a couple of thermal oversights. As background, 2.5 years ago I started driving an electric car. This isn't my house, by the way, just my car visiting Arizona's famous Biosphere 2. Well, to wheel, so they say, you'll use less energy per mile driving an electric car than you would if you drove an internal combustion engine vehicle. My idea was to go one better by installing a 5-kilowatt photovoltaic array on my house. And yes, this is my house, which I expect you recognize by now. This chart shows that over 2.5 years, my solar panels have produced 67% more energy from the sun than I have used in the electric vehicle. Not the house, just the vehicle. Perhaps you've read that Tesla's supercharger stations for long-distance road trips in their new Model S are each sized with local photovoltaic arrays such that they're anticipated to be net grid positive. Now, I'm not going to claim that I gave them the idea, but I did it before they did it. Anyway, you've possibly heard the term range anxiety, which is a big hurdle EV advocates have to overcome, maybe bigger than overall energy consumption at the wall or the well. This chart is my history of battery-to-wheel efficiency over 2.5 years. It shows no clear correlation between seasonal temperature variations and overall cost efficiency. On average, when it comes to delivering battery energy to the road, I've gotten 4.0 miles per kilowatt hour, which comes out to 286 miles per gallon for $5 a gallon gas, except that doesn't take charging losses into account. Range may depend only on battery size and how efficiently the energy is delivered to the road, but operating cost introduces the additional factor of charging efficiency. This chart shows my wall-to-wheel history, whose average over 2.5 years comes out to only 2.5 miles per kilowatt hour, or a measly 179 miles per gallon at $5 a gallon. But what I found, and you see it clearly in these graphs, is that wall-to-wheel energy consumption is highly temperature dependent. Unfortunately, I live in Phoenix, Arizona, and we're at the high temperature end of this chart. They didn't mention this factor at the beginning, which could really burn me up, except that my effective mileage is still pretty terrific. It's possible, of course, that maybe they really didn't know. But they do now. I send them these charts every couple of months. As an aside, I've got to tell you a funny story about collecting all this data. I grew up in a Methodist pastor's very frugal household. The car I learned to drive was a 61 VW Beetle, which some of you may know didn't even have a fuel gauge, just a kick lever on the floor that gave you a 1-gallon reserve, if you'd remembered to kick it back over the last time you got gas. Talk about range anxiety. Anyway, I grew up having learned to keep records of when you got gas, how much you put in, and what the odometer said when you did, mainly so you could always have a rough idea of how much farther you could go before you had to kick that lever over. In short, from about 1975 through 2010, spanning a dozen different gasoline-powered vehicles, I have continued compulsively to log all my gas purchases, tracking miles per gallon through tire changes, the seasons, etc. So when I decided to get this all-electric vehicle, my kids said, "Gee, Dad, no gas tank. Whatever are you going to find to write down?" I should add, a few years ago, my doctor did officially diagnose my condition as data junkie. So to get back to the original EV story, Tesla's liquid-cooled battery packs have all held up really well in the Arizona heat, quite unlike Nissan's experience with inadequately cooled Leaf batteries. What Tesla missed is that their universal mobile charge adapter doesn't work so well when the sun shines on it. I'm now on my third UMC. Along the way, though, someone pointed out that in the manual it says, "Do not operate in ambience over 105 Fahrenheit. Is this a joke? Anybody who's lived in Phoenix can tell you how hot things get when the sun is shining, and from June through August, even the nighttime temperature inside my garage might not drop below 105. Honestly, you can't design and market automotive equipment in Phoenix and say not over 105 Fahrenheit. Taking obvious advantage of my employer's resources, I quickly provided Tesla with careful IR images of various vehicle and equipment situations where temperatures were in excess of 170 Fahrenheit. Now that we know the real issue, here's a photo of how easy it is to beat the heat, so to speak. But what really burns me up is they didn't provide a towel in the trunk. Before I drop all the way down to the semiconductor packaging scale, I have two more energy system-related examples to talk about. The first goes back to 1989, when Pons and Fleischmann astounded the world with their claims of fusion energy in a test tube. This really grabbed my attention, as only 10 years earlier I had completed my master's in mechanical engineering at Caltech. My main interest then had been in fusion research. Very serendipitously, in 1989, Motorola began offering what they called Eureka Fund dollars, basically company internal research dollars targeted at what might otherwise be considered wild hair ideas. This certainly qualified. And for 6 months, I engaged in cold fusion research. This meant I got to set up potentially hazardous lab experiments. Even my 7-year-old daughter had nightmares about me blowing up the city. I purchased heavy water, got to play with lithium, and wore a radiation badge. Gleaning what little we could from what had been made known public at the time, I had to design my own cold fusion cell with an expensive pure platinum anode and a pure platinum cathode. I designed a custom calorimeter to monitor total energy in and out of this cold fusion cell. Should we ever have had any anomalous events, we had secured the services of an outfit that could assay for tritium, a supposed byproduct of a successful fusion reaction. Though history has since judged cold fusion a scientific blunder at best and outright fraud at worst, we did have one anomalous event. One morning when I checked the calorimeter status after the previous overnight run, I discovered that the internal cold fusion cell had apparently ejected a significant quantity of the lithium hydroxide solution, as if it had boiled over. In several months of operation, nothing like this had ever occurred before, nor did it ever occur again. However, chart traces showed no evidence of temperature spikes, and voltage and current traces showed no evidence of excess input energy. I did a number of calculations based on my known error limits and concluded that if anything had happened, the amount of energy it represented would have been within the error bars of cumulative energy balance over the entire runtime of the apparatus. In other words, my cell could possibly have been a battery that stored some energy and then released it all at once within the error bars. But there was no conclusive evidence of excess energy at all, even if the cell had boiled over. I mention this as an example of the need for careful analysis of error limits, which if I had not done could have misled me and wasted considerably more time and funds. I suspect this sort of thing happens all too often. This next example is quite contemporary. There's a small outfit in New Jersey currently working on a hot fusion technology known as dense plasma focus, or DPF. For a mere $1 million or so, they've constructed a prototype pulsed fusion reactor, and they're presently engaged in working it up to the energy break-even point. Their proton-boron reaction is very clean because it yields 3 very energetic helium nuclei, but no neutrons. I am really jazzed that this DPF fusion concept is going to succeed and ultimately turn the world's energy production system on its head, non-renewability notwithstanding. The reason I bring them up here, however, is perhaps because due to their focus on the fusion side of the science, I'm afraid they've understated a fairly significant thermal obstacle to their first-generation reactor design. They're projecting that a neighborhood-sized reactor, 5 megawatts electric, enough to power about 100 homes, will be 37% efficient. And it'll be small enough even to fit in a garage. Okay, that's all well and good, and in fact the beryllium core of the reactor itself could be as small as a bread box, which clearly will fit in your garage. Here's the rub. To get that 5 megawatts electric, your waste heat is 8.5 megawatts. In other words, there's even more waste energy than the amount of energy you're generating to spread across 100 houses. And you're going to try to dissipate all that waste energy from a single garage? Well, they want to keep it simple, like using free convection air cooling. I made some quick estimates of the surface area required for some pretty extreme boundary conditions. For instance, suppose you allow a 350 degrees C temperature rise of the cooling air. You'll then need only 32 cubic meters per second of airflow and only 2,600 square meters of fin area. Not that I recommend injecting any amount of 375 C degree air into the neighborhood sky. I do fear that engineering a garage-sized reactor may not be as easy as they're assuming. For instance, maybe they should reserve free convection cooling for later when the reactor efficiency is up to 55%. Granted, there's still a few big steps away from having to get serious about these details. But speaking as somebody whose job it is to remove excess heat from electronics, this looks like an interesting challenge. In fact, it's a bit worse than I've painted in this quick outline because remember, I said the reactor core itself is only about the size of a bread box. Wrap that inside a Rogowski coil and an X-ray absorber, and you still got something with a total surface area of maybe a couple of square meters. So we're talking waste heat energy densities on a rough ballpark of 3 megawatts per square meter. To put that in some kind of perspective, energy flux density at the surface of the sun is only 60 megawatts per square meter. But remember, the sun gets to run at 5,000 kelvins, which is a bit hotter than you want inside your garage. That really burns me up. Okay, let's move on down to semiconductors. Here's an LDMOS device from a few years ago. Not this particular device, but one that we were in the initial stages of engineering, was projected to produce chip surface flux densities of about 60 megawatts per square meter. Do you recognize that number? Again, we weren't going to have the luxury of letting it blow its way cool at 5,000 kelvins like the sun does. We were going to have to keep it down around, say, 200 C. Of course, its active area was only a very small fraction of a square millimeter, so our total energy wasn't all that much, maybe just 20 watts or so. But customers and chip designers seem to have this tendency to think that they can keep shrinking things, and I keep telling them that's fine, but if they don't shrink the power per square millimeter at the same time, they're going to have trouble. When they don't, it really burns me and their devices up. Thermal characterization itself also brings me up against some persistently frustrating issues. Take thermocouples, very simple temperature measuring devices we use all over the place. The most obvious problem, I think, is that when the thermocouple itself is as large as the device you're trying to measure, you're going to cool it significantly. T-type thermocouples, for instance, are particularly bad this way because one of the two wires is copper. Others, K for instance, are much better in this regard because both wires are relatively poor thermal conductors. In device characterization, we always make internal device junction temperature measurements using internal electrical characteristics of the device itself. But for external temperature measurements, the case top, for instance, we have to use another method. So we sometimes first make internal measurements leaving off external thermocouples. And then we'll mount an external thermocouple and repeat the measurements, getting both the internal junction temperature and the case temperature. We can then see if and how much that internal junction temperature changed due to the presence of the thermocouple. And then we know whether the thermocouple itself contaminates the measurements. It's often a very measurable effect, and it gets more so as the packages continue to shrink. If that's a problem, how then do we measure the case temperature? Infrared? Well, okay, but as I've already pointed out, that introduces its own share of difficulties. Another thing about thermocouples is a common misconception of exactly where the temperature is measured and how, therefore, you might calibrate a thermocouple. The fact is, a thermocouple does not measure the temperature at the junction where the two dissimilar metals come into contact. The junction itself simply completes an electrical circuit, providing a common reference point for two EMFs that vary differently with temperature in the two different metal wire materials. Thus, if I've got a thermocouple inside a temperature chamber, the inside chamber temperature is actually measured in region C in the diagram, which is where the temperature gradient appears as the wires emerge through the door from the hot interior to the outside. To truly calibrate this thermocouple, then sticking the junction into a known temperature bath doesn't do squat. If the gradient during the calibration procedure occurs 5 centimeters from the junction, but if in my typical use the thermocouple gradient occurs anywhere from ½ a centimeter to 50 centimeters from the junction. Another thing that really flabbergasted me was when I discovered that our Cal lab was doing a quadratic fit of thermocouple error at 3 points. I trust you all know that you can fit a straight line through 2 points. Better, you can fit a straight line and get some idea of error by using 3 points. So if you're willing to give up any sense of error, you can fit a quadratic through just 3 points. But can you fit a quadratic through just 2 points? Not a unique one. And what then if we don't even bother to measure the third point, but just assume it? Can you sense that this is a rhetorical question? These errors, not knowing how a thermocouple actually measured temperature, and not knowing enough about curve fitting, form the entire basis of the Thermocouple Cal Lab's business. This really burned me up. And should I add, I quit purchasing the services of that lab. Allow me to interject here a real-life consumer example of why this stuff matters. Sometime back in the 80s, I bought a Plymouth Voyager minivan. One fateful day I got in, started it up, and became aware of an electric motor running sort of sound. It took a minute to identify that it was the rear window washer pump motor running, about as long as it took to run the washer fluid tank dry, and danged if it didn't keep running as long as the ignition was on. The next day I took the car into the dealer and they replaced the washer control module in the dash, what I thought to be a simple on-off button. The car was still under warranty, so it was a bit inconvenient, but that was that. Then a couple of years later it happened again, exact same symptoms, only this time it was out of warranty and it cost me $110 to again replace the washer button module in the dash. A couple of years later, while I was on vacation out of state visiting my brother-in-law, it happened again. This time, I popped the module out of the dash and inspected it. There was a Zener diode in there that had charred and cracked in two. With my brother-in-law's help and a good magnifying lens, we were able to read enough of what was left of the part number on the device to determine the Zener's breakdown voltage. We then ran down to the local Radio Shack and for a couple of bucks bought a half-watt version of the original 1/8 watt diode and swapped it out. The problem never happened again. This is a textbook example of a protection device that apparently gave its life doing its job. Kind of like it was designed to, sort of. It was just a bit too small for the real-life conditions it should have been designed to handle. Let me bring this home now with a brief encounter with my favorite pet peeves about semiconductor characterization, and customers especially who don't understand thermal numbers. You all know what theta JA is. It's the magic number that comes on a data sheet that tells you how hot the junction of a device will run, given ambient and PD, power dissipation. Seriously, I teach half-day seminars on this one subject alone. There are about 6 reasons that the theta JA value you get on a data sheet isn't worth the bandwidth of the Ethernet you received it on. And very often, maximum device power, PD, is simply calculated from theta JA, assuming 25C ambient and whatever the max rated TJ is. What burns me up is that people insist on using these numbers to actually design the device into their system. Or maybe what's worse, they don't buy it from us because somebody else's theta JA value looked better. And there's the occasional person who thinks that ambient means board temperature. Big mistake. Another oft-abused number is theta JC, which gets you past maybe 4 of those 6 problems with theta JA, but introduces its own generally unstated issue, namely, where exactly is the case represented by the C in theta JC? If you think that the case top of a plastic package is what theta JC refers to, I've got bad news for you. As long ago as 1995, JEDEC tried to help us out by introducing a new term, psi JT, which might be a help if people would familiarize themselves with the concept. Here's another pet peeve. I probably ask this question on average once a week. How many amps can this device handle? My main beef is that as a thermal guy, I work in watts, not amps. Never mind that they don't tell me anything about their board or environment. Invariably, we go back and forth a couple of times before I get the information necessary to answer their question. Another peeve is those normalized transient thermal response curves, where they have divided out the steady state value of the curve, and if you're lucky, they gave you that value for reference. As if somehow the starting in of the curve didn't depend on die size. Probably the other most common conceptual issue that burns me up all the time is one I've already touched on in a couple of the earlier examples. If you know your total PD of an electrical system, you can already draw some broad conclusions about how big it's going to have to be, simply to dissipate that much thermal energy to the environment surrounding the system. It's like sticking a 5 megawatt fusion reactor in your garage. The details of whether the beryllium core is going to melt obviously matter at some point, because you can't get enough heat through the surface area of a bread box without exceeding the melting temperature of beryllium. But unless the surface area of your garage is as big as a football field, you'll never get rid of the wasted 8.5 megawatts, even if you solve the core temperature issue. Similarly, the specific semiconductor package you choose might be an issue in exceeding max TJ at a very local level on a PCB. But remember, your PCB has to be large enough to reject all the heat from all the devices, regardless of their temperature. If it can't, the problem isn't theta JA of any particular device. The problem is your PCB is too small. A product manager friend of mine at ON recently put it in this rather crude but unforgettable way. If you're in a big swimming pool by yourself and you have to pee in the pool, you won't even notice the water temperature go up. But if you're having a big pool party and 50 of your friends are in the pool with you at the same time, the informed, terms properly defined, and practitioners adequately trained. Now, I've discovered that when I begin working in a new arena, very often there are relatively simple things I can fix that have a big impact. I don't know if it's a particular peculiar way I have of looking at things, or if it's simply the phenomenon of getting a new pair of eyes on a problem. A former supervisor of mine had this take on it: luck and skill pay the same. Either way, let me wrap up my talk today with two examples from early in my career. When I first took the job of managing the thermal lab for Motorola's ASIC division in Chandler, Arizona, it came with a wind tunnel. To measure airspeed in the working chamber, this wind tunnel used a hot wire anemometer, of which I had heard but had no experience. Now, in some labs, not ours, but others even within Motorola and many around the country, it's necessary to measure moving air device characteristics at elevated temperatures. Curiously, a hot wire anemometer measures airspeed using the exact same physics that cool a hot package, sort of in reverse. It basically infers how much air is flowing based on the cooling effect on its heated element. Of course, everyone realizes that as air temperature goes up, density goes down. So it's no surprise that the anemometer's operating manual referred to the necessity of making corrections to indicated speed if the air temperature was elevated, and it showed how to make these corrections. Indeed, air density drops by a whopping 35% over the range 0 to 100 C. Even under relatively modest changes in temperature, say 25 to 60 C, you no doubt want to account for this effect, it being about 12% based on the published temperature density method alone. As I got to thinking about it, however, I realized that for a heat transfer-based anemometer, accounting for this temperature density change alone was incomplete and quite possibly inadequate. In fact, it's generally true that as temperature changes, not only does density change, but so do specific heat, viscosity, and thermal conductivity, all four properties of which figure prominently in boundary layer heat transfer, the crux of the hot wire method. So I went back to the textbooks, carefully analyzing the combined effects of these variables on boundary layer flow and heat transfer coefficients. And I was reminded of these effects. For air, as temperature ranges from 0 to 100 C, density decreases 35%, as I already mentioned. It does turn out that its specific heat is essentially constant, but air viscosity increases 27%, and its thermal conductivity increases 32%. Astoundingly, applying the proper exponents to each of these properties in the heat transfer relation, the net effect of the four variables cancels out to within about 1% over the entire range. So, luck is making no correction out of ignorance. Skill is knowing that you shouldn't. Here's my other all-time favorite wind tunnel story. 1990, and I've just arrived in the thermal lab of Motorola's ASIC division, my new job meeting Candy, the technician who's been doing this job for a couple of years. I'm looking at this nice wind tunnel with its nice hot wire anemometer that I'm soon to learn doesn't need temperature corrections either. Its placement is directly in front of the PCB, casting its wake across the PCB and the DUT. I ask, aren't you worried that the anemometer is going to mess up the airflow across the PCB? Look how it's right in line with the DUT. She says, not at all. The air blows the other way. So my next thought is, then aren't you worried that the PCB is blocking the anemometer and messing up your airflow measurement? But instead I do a double take. Look closely at this picture of the wind tunnel with me. Now, the last time I was up close to a wind tunnel was probably back in school in 1977. But I think I recognize a flow straightener when I see one. And besides, there is this huge fan at the other end that you probably don't want blowing swirly air into the chamber. So I say, Candy, are you sure the air blows from right to left? Sure, I'm sure, she says. The fan blows air into the chamber. Really, I say. Turn it on, I gotta see this. So she turns it on, and I hold a piece of tissue in front of the fan grill where it's supposedly sucking air into the chamber. The fan blows it right out of my hand into the room, away from the test chamber. This fan blows, or maybe sucks, depending upon your perspective. Candy has this look of utter astonishment on her face. Dang. Luck is having problems like this drop into your lap. Skill is recognizing them when they do. Over the years since then, it's definitely not always been that easy, but I do like to tell people, when I started this job, they didn't even know which way the wind was blowing. It's been my pleasure telling you about it. Thanks for listening.
We would like to have a call for final questions. Please enter any last questions you may have in the navigation pane. We have received quite a few inquiries on where to get additional information on this topic. There is a vast amount of content found on our website, www.electronics-cooling.com. You can also email us at info@electronics-cooling.com with specific needs, and we can direct you accordingly. Roger, here's a question for you. You referred to the sun delivering as much energy in an hour as humankind uses in a year, but then you started talking about power consumption. Are you confusing energy and power?
Well, that's actually a good question. Let me move back. I'll just throw up this slide 8. I reported global energy consumption and solar energy delivery in watts, and that's energy per unit time, or power. I somewhat carelessly implied that they represent total energy used in 2013. So to be perfectly clear, that 2013 figure would be the average global power consumption by humanity if you took the total energy projection for 2013 and divided by the number of seconds in a year. Either way, the ratio comes out to 0.016%. In 2013, we will use 1 hour's worth of the solar energy striking the planet. Hope that answers the question.
We have another question. Did you say thermionic coolers are perpetual motion machines?
Well, I may have been a little sloppy. No, I didn't mean to say that. Let me find this slide here. This was just kind of showing an energy, sort of an energy audit through a thermionic cooler. What I was trying to say is in thermodynamics, we learn about perpetual motion machines of type 1 that violate the first law of thermodynamics. That would be like that zero-cogging generator I talked about on wind turbines that creates energy or outputs more energy than it takes in. A type 2 perpetual motion machine is one that doesn't violate the first law, but it does violate the second law. That is, it decreases entropy. In a practical sense, anything that moves heat from a cold place to a hot place is asking for careful scrutiny of the second law. But there are plenty of actual machines capable of doing this, traditional heat pumps, for instance, such as the hybrid water heater in my garage, or thermionic coolers. Technically speaking, a heat pump or a thermionic cooler doesn't violate either the first or second laws, and in fact they couldn't or they wouldn't work. The problem is people seem to think of them as if they violated the second law, that somehow you can lower the temperature of something without making the temperature of something else go up by an even greater amount. That's where we often run into trouble in the semiconductor world. You can't make an overall device more efficient, that is, run at a lower temperature, simply by inserting a thermionic cooler. You have to give up something. As an electronics cooling guy, what I'm giving up is that there's more total energy to remove than I had before. So unless it's just a very small portion of the silicon that I'm trying to cool at the expense of total waste heat, I'm actually worse off by adding a thermionic cooler.
Here's a question on thermal response curves. I didn't understand what you were getting at with these normalized transient thermal response curves. Can you be more clear?
Yeah, let me try again. I'm going to zip up to, see, that was slide 90 here. Let me find that. Yeah, unfortunately, I didn't really have time to do this justice. It was mainly just one of my pet peeves. The problem is that the short-time thermal transient response does, in fact, depend very strongly on the die size or the device, the active area of the device, and it really doesn't depend on anything else, not at short enough times. When you normalize the heating curve by dividing by the steady state value, what you're saying is that the entire curve from short time to steady state goes in proportion to the final value, which is patently ridiculous. In that lower chart, you can kind of see if you took the three curves above, divided each one by its final power, they all end up at the same point on the right, but they start at different points on the left. In other words, just because you mount a device on a super heat sink such that the steady state theta JC drops, say, 80%, the short time response at 1 millisecond shouldn't be any different at all. But when you normalize the curve, it makes it look like the short time response just dropped by 80% too. And the only way to do that would be by making the die size bigger, which obviously didn't happen just because you divided the curve. That's one of my pet peeves. Normalized transient response curves should be outlawed.
We have another question. I never heard that about not needing to adjust hot wire anemometer reading for elevated temperatures. Why not?
Bad luck. Since we didn't use any elevated wind tunnel data in my own lab, it really was just incidental. I didn't want the guys at the other Motorola labs who did use elevated temperatures in their wind tunnels, so I didn't want them to make the same mistake. So I published one paper on the subject in a Motorola Internal Technical Symposium in 1992. As I recall, I ran it by the anemometer manufacturer, and I think they said they'd check into it and get back with me, but I don't think I ever heard anything back from them. Oh well.
We have received some... Thank you, Roger. We have received so many great questions that we will try to address in the future. Roger, thank you again for your time and expertise. Webinar attendees, if you have any more questions that we didn't answer here, please send us an email at info@electronics-cooling.com. A recording of this webinar will be available on our website, www.electronics-cooling.com. We will also send a link to all participants shortly. Thank you for attending.
All right. Thank you for coming.